Hello, welcome. In this short video, let us look at the sharpness of a likelihood function. The reason why we want to look at sharpness is because it can be seen as an indicator of accuracy of the estimator derived from maximizing the likelihood function. That is, consider this observation model given by x of 0 equal to a plus w of 0, where w of 0 has a normal distribution with mean 0 and variance sigma square, that is white Gaussian noise. Then the model for the observation x of 0 is given by a normal distribution with mean a and variance sigma square. Then the likelihood function L of a is given by probability of x of 0 with the parameter a. Then the log likelihood function L of a, the lowercase l of a, is given by the logarithm of probability of x of 0, the probability density function at x of 0 given the parameter a. Therefore, the log likelihood function L of a is equal to, using the definition of the normal density, we have logarithm of the PDF at x of 0, which is 1 by square root of 2 pi sigma square exponential of minus x of 0 minus a whole square divided by 2 sigma square. So logarithm of this PDF becomes minus logarithm of square root of 2 pi sigma square minus x of 0 minus a whole square divided by 2 sigma square. So this is the log likelihood function with the parameter a. Now the sharpness of the log likelihood function, which basically characterizes the accuracy of the estimator, can be seen as the curvature of the likelihood function. That is, the sharper the peak of this likelihood function, the accurate is the estimator of the parameter a. So the curvature can be quantified by using the negative second derivative of the log likelihood function. So we can determine this value by first determining the first derivative of the log likelihood function is equal to the derivative of logarithm of 2 pi sigma square power 1 by 2 is 0 with respect to a, and this is minus 2 x of 0 minus a divided by 2 sigma square to minus 1. Therefore, this is equal to x of 0 minus a divided by sigma square. Therefore, the second derivative of the log likelihood function is equal to minus 1 by sigma square. That means the negative second derivative of the log likelihood function is equal to 1 by sigma square. And for single observation x of 0, the estimate is the observation itself, and therefore the variance of the estimator a hat is the variance of the observation, which is equal to sigma square. Therefore, for a single observation, the variance of a hat is equal to minus 1 by minus of the second derivative of the log likelihood function, which is equal to 1 by minus dou square by dou a square of logarithm of the probability density function at x of 0. So this is the, so for a single observation, the variance of the estimator is equal to inverse of the negative second derivative of the log likelihood function. For this example, clearly the sharpness factor or the negative second derivative is equal to 1 by sigma square, which is basically independent of the observation x of 0. But in general case, this sharpness factor usually depends on the observations, and so we have to consider an average value of this negative second derivative, that is an expectation of the negative second derivative given by minus second derivative of the log of the probability density function at x of 0. And obviously the expectation is with respect to the probability distribution of x of 0. And we will see that in the Cramer-Rao bound term basically will constitute the, or will be the denominator of the bound on the variance. Thanks for watching.